Hello, this video we're going to talk about covers section 9.1 from your textbook, and it's basically a review of the square root and how to simplify expressions involving a square root. Also, we're going to talk about finding higher roots like cube roots and fourth roots. And then at the end, we're going to talk about some properties that we can use to simplify radical expressions. And we're also going to talk about the domain of radical expressions. So let's begin by talking and reviewing the basics of square roots. Let's start with the definition. So the basic definition of a square root is that a is the square root of a number b if b squared is equal to a. And that concept is basically what we use to figure out square roots. For example, the square roots of 25 are 5 and -5. Why? Because of this definition. Because 5 squared equals 25. And also because -5 squared is equal to 25. So we're asking ourselves, when we're trying to find a square root, we're asking ourselves what number squared is equal to the value inside the square root. A couple more terminology type things. Right here we have a radical expression. Anytime we have the square root sign and a b or anything that could be underneath the square root, that's called a radical expression. And when we use that assemblage, we're talking about the principal square root, or in this case, the positive square root. Because as we just saw in that last example, what are the square roots of 25? There's actually a positive square root and a negative square root. Well, when we use this symbol, we're just talking about the positive square root. The actual sign that we use to represent square root, we call that a radical sign. And then the number underneath, and it's not always a number, it could be a variable, the number of variables underneath the radical sign is called the radicand. And so we can take a look at a couple of simple examples here. The first one is, what is the square root of 81? Well, the square root of 81, we should all know this, is 9. And going back to that definition, this is because 9 squared is equal to 81. So 9 is the principal square root of 81. Now if we want the other square root, the negative square root, we actually have to put a negative on the front of the square root. So in this case, the negative square root of 81 would be -9. Okay, we can also take the square roots of fractions. This is going to be, the square root of 9 over 49 is going to be 3 over 7. There's a couple ways to think about this. One reason, using the definition above, we can say this is true because 3 over 7 squared is 9 over 49. Or we can even think about taking the square root of the top and bottom individually. The square root of 9 is 3 and the square root of 49 is 7. We can also talk about the square root of 0, which is 0. That, again, because of our definition, this is because 0 squared equals 0. And then the last one, square root of a -9. Are there any numbers? This is the kind of question you're asking yourself. Is there anything that can be squared that will give us -9? And the answer to that, I hope you will agree, is no. Because when you square something, it always turns positive. So in this case, we would say that this guy, the square root of -9, is not a real number. And at the end of this chapter, we will talk about what non-real numbers are. We call them imaginary numbers, but we're not quite ready to get there. So for now, we'll just say it's not real. Okay, now let's move on to talk about square roots when we have variables involved. Now, strictly speaking, the square root of a squared would actually be the absolute value of a. We would think it would probably be a, but it's actually the absolute value of a. And this is because we have to account for the fact that when we have a variable, it can be negative. And so if a is positive, for example, then this works out. But if it's negative, then this could potentially over here be a negative. So that's why we have to have the absolute value. Now, most of the time we never include the absolute value, and the reason why we don't have to include it in most of the problems that we will be talking about is because we assume that a is a positive real number. Pretty much all the problems we're going to assume that a is a positive real number. In fact, the directions of your problems will specifically state assume that all variables represent non-negative real numbers. So we're not really going to worry about this too much. We're just going to assume that they're non-negative real numbers, but they could be. Just keep that in mind. So if we do assume that a is a positive real number, then the square root of a squared we are going to say is just a. We do not have to worry about the absolute value. So if I'm trying to find the square root of 64x to the 24th, the square root of 64 is 8, because 8 squared, or 8 times 8, is 64. And then for the variable part, we have x to the 12th power. That is because x to the 12th times x to the 12th is equal to x to the 24th. Remember, when we multiply exponents, we add the powers. 12 plus 12 is 24. So if you think about this next one, the square root of 16 over 9 is 4 over 3. And then what's the square root of x to the 12th? It's x to what power? Well, it's got to be the 6th power, because x to the 6th times x to the 6th is x to the 12th. Now, one thing that you should have noticed when we're going through this example, and you may have learned this before, is when you're taking square roots, the power basically gets divided by 2. 24 divided by 2 is 12, and then when we have this exponent, x to the 12th, if we divide 12 by 2, we get 6. So that's kind of a little shortcut sometimes people like to think about. Let's also talk about how we would evaluate a square root on a calculator. And I want to try to take the square root of 75. The square root button is over here on the left hand side. You have to hit the second button to get it because it's with the squared button. So if you hit the square root of 75, that's equal to 8.660 if we round to the nearest thousandth, which is the third decimal place, tens, hundreds, thousands. So this is going to be approximately equal to 8.66. Okay, so you should be able to do the next one. Go ahead and try the next one. If you do the square root of 27, you get 5.196. 5.196. If you haven't seen the little squiggly equal sign, that means approximately equal. We're not exactly here because we're rounding. This is approximately equal. Okay, so now would be a good time to go ahead and start your self-check. If you go to the last page, you should be able to do the first two problems. So go ahead and pause the video and try those, then come back when you're done. Alright, so we've reviewed square roots. Let's now talk about higher power roots, like the cube root or the fourth root, and it goes on beyond that. But if we talked about, for example, the definition of an nth root, that's any possible root n. A is the nth root of b if b to the n power is equal to a. So it just kind of extends our definition for square roots. I like to write this table. You're going to maybe want to use this as you're doing your homework. If we have our square roots, our perfect squares are things like the square root of 1. We know that's equal to 1 because 1 squared is 1. Square root of 4 is 2. The next perfect square is 9, which is 3. The next perfect square is 16, which is 4. Square root of 25 is 5. And then the square root of 36 is equal to 6. Those should hopefully be familiar to you. Notice if you go down the line on the right hand side here, 6 squared is 36, 5 squared is 25, and so on. And we're going to have the same thing then for cube roots. We have the cube root of 1 is equal to 1. Cube root of 8 is equal to 2. Cube root of 27 is equal to 3. Cube root of 64 is equal to 4. Then we also have the cube root of 125, which is equal to 5. And so again, 5 cubed is 125, 4 cubed is 64, 3 cubed is 27, and so on. Then we can talk about some of the fourth roots. The fourth root of 1 equals 1. Fourth root of 16 is equal to 2. Fourth root of 81 is equal to 3. And we could go on. But this kind of gives you an idea of some of the common roots. One little note here, only odd roots can have negative radicands. For example, the square root or the cube root, that's an odd root because it has an index of 3, which is an odd number. I can take the cube root of a negative 27. That's equal to negative 3. Why? Because negative 3 cubed is equal to negative 27. A negative times a negative times a negative. A negative times itself 3 times gives us 3 negatives, which is equal to a negative when we multiply. So if we look at some of these other examples, the cube root of 1,000 is going to be 10. This is because 10 cubed equals 1,000. Hopefully that makes sense. What would the cube root of negative 8 be? Again, here we have a odd index, so we can have a negative radicand. The answer here is negative 2, because negative 2 cubed equals negative 8. And we don't have to write, when you're doing your homework, you don't have to write out this because. I'm just putting this in here for your reference so you know where I'm getting these answers from. Okay, now here we have the fourth root. This is an even index, an even root, the fourth root of a negative. Is that possible? No, it is not. This is a non-real number. And then the last one, we know that the fourth root of 16 is 2, because 2 to the fourth power is 16. And then for the variable b to the 24th, the fourth root of that is b to the 6th. That is because 2b to the 6th raised to the 4th power is 16b to the 24th. In other words, b to the 6th times b to the 6th times b to the 6th times b to the 6th is b to the 24th. And notice the shortcut here. When we took square roots, we divided the power by 2. Well, when we take fourth roots, you divide the power by 4. So 24 divided by 4 is 6. And that's how we do higher root radicals, higher degree radicals. The next section is how do we multiply radical expressions? Well, we're going to use this property. We're going to use this property that says that if we multiply a root times a root, we can combine the radicands and multiply them underneath the same root. So if I'm going to do this first problem, what we're going to think about here is we're going to think about taking, okay, the numbers outside the radical, that's the 9 times the 8, and then we can multiply the numbers inside the radical, the 12 times the 3. So the numbers outside, the 9 times 8 multiply to give us 72, and the numbers inside, the 12 times 3, gives us 36. And then you always need to ask yourself, can you simplify the radical? And in this case you can, because the square root of 36 is 6. And 72 times 6 is 432. So if you look at the next one, these roots, the root indexes are both 3s, so we can multiply them. And it becomes 3 times 9 is 27, and then a to the 4th times a squared is a to the 6th, which I can take the cube root. The cube root of 27 is 3, because 3 times 3 times 3 is 27, and the cube root of a to the 6th, well, we just divide that power of 6 by 3, which gives us 2. So we have 3a squared. So we've now done enough where you should be able to go ahead and look at the next two examples. You should be able to do C and D in your self-check. If you want to go ahead and pause the video and try those, and then we'll come back and do the last page here. Alright, so welcome back. The last property here that we're going to talk about is the quotient property for radicals, and that means if we have a radical divided by a radical, we can combine them underneath the same radical. So in other words, this example here, since we have a cube root divided by a cube root, I can make this 1 cube root, and I can divide 40b to the 7th by 5b. And when I divide, things get a lot simpler, because 40 divided by 5 is 8. Then I have 7 b's on top and I have 1 on the bottom. One of those b's on the bottom cancels with one of the 7 on top, leaving a b to the 6th, and there is no more denominator. Of course, the cube root of 8 is 2, and the cube root of b to the 6th is b squared. Divide that power of 6 by 3, you get 2. And that's how you can apply the quotient rule. We can also talk about if we have a radical function, that's a function that has a square root or a cube root in it, or a fourth root, or so on. If we have a radical like that, we can evaluate the function. So, for example, with this function, if I wanted to find an f of 20, I would take wherever there was an x and plug in a 20. So this would be a 3 times 20 plus 4 minus 17, which is 3 times 20 is 60, plus 4 is 64. Square root of 64 is 8, so we have 8 minus 17, which is equal to a negative 9. So when x equals 20, y equals negative 9. So if we're talking about functions, of course the other thing we want to talk about is the domain of a function, which I'm sure you're all very happy to have back in our topics. The domain of a function is remember, is all the x values that you can input into the function. It's all the possible inputs. All possible inputs, or x's. So the question we really need to ask doesn't matter if we're taking and finding the domain of radicals involving even roots or radicals involving odd roots. And the answer is yes, it does matter. Because remember, you can take the square root of a positive number. Yes, you can do that. But can you take the square root of a negative number? The answer is no. We said that that was not real. It's not real. However, for cube roots, for example, that's an odd root. A cube root of a positive, like 8, that does work. That's equal to 2. And I can also take the cube root of a negative. That would be equal to negative 2. So when we have odd roots, we don't need to worry about restricting the domain. You can have odds or evens go into here. It's only when we're having even roots, like square roots or fourth roots, that we have to worry about negatives. So I have two examples here. One, both involving square roots. Find the domain of a radical function. Well, since this is a square root, remember I can only take the square roots of positives. That means that the radicand, remember the radicand is the part underneath the square root, the radicand has to be positive. Which means that x plus 4 has to be greater than or equal to 0. I should say actually it has to be positive or 0. Because you can't take the square root of 0. You just can't take negative. Well, if I solve this, I can subtract 4 from both sides. And that gives me that x is greater than or equal to negative 4, which means that the domain is everything from negative 4 to infinity. So in this next example, we basically have the same thing. It's a little bit more involved because it has this 23 on the end. There wasn't anything outside the square root in example A. But in this example, we're really just concerned with the same part. We're concerned with making sure that the radicand, the part that's underneath the square root, that 2x minus 9, that it is only positive. So we're going to say that. We're going to say, okay, 2x minus 9, again, has to be greater than or equal to 0. And we solve for x. So in this case, we need to add 9 to both sides. And when we do that, we get 2x is greater than or equal to 9. One more step to finish isolating for x. We need to divide by 2. So the 2's divide out. And finally we get to x is greater than or equal to 9 halves, which we write that in interval notation, looks like 9 halves, comma, infinity.